So the topic of my presentation tonight is naval crew size and habitability, and where is the future? And just for reference, this is the same presentation that was given recently at the Warship Conference in Adelaide, which is a RINA conference as well. Okay, so Richard has already alluded, but Taylor Brothers is a fourth generation family business. Basically, marine engineering is the specialty. It's started in 1936 as a shipbuilder, actually building mainly timber craft. But today, it's really a specialized marine engineering company, which includes project management, engineering, design, fabrication, build, and electrical, mechanical, and logistic support services for defence, offshore oil and gas, Antarctic, and marine science, and the general marine industry in Australia and overseas. So, an overview of our capabilities. Obviously, we work for the Antarctic division and vessels that go to Antarctica. We work in the defence sector for new builds and upgrades. We do general design and engineering. We specialise a lot in marine accommodation, for offshore and general shipping. So an outline of the presentation tonight, obviously the introduction. I will look at habitability and accommodation rules within the Navy. I'll look at current Navy surface combatant crew sizes and examples of the increase in crew size and a particular study that was done recently. I will look at impact of crew size on ship design and ship systems, particularly for the naval vessel. I will look at crew size in the commercial sector. Sorry, I've just got to let somebody in the room. Sorry about that. Design differences between commercial vessels and warships. Some realistic change proposals and impact on ship capabilities, conclusions, and questions and answers. So in general, habitability. In general, habitability rules for Navy vessels and for surface combatants. The main rule set is the DEFOS. Hello, is somebody trying to speak?
Yeah. Who says they need help?
Okay, I'll continue. DEFOS 5000, Volume 8, Part 1, accommodation requirements is the Australian rules. And then the other rule set current is the DST Group TR 3550, which is the revised maritime physical accommodation guidance for the Royal Australian Navy. And a subset of this rule set is the DST Group TR 3564, which is the anthropometric guidance for the Royal Australian Navy. So it should be noted, these are the Australian rules for naval servicing combatants, but currently in our fleet, there's no servicing combatant is actually designed to meet these rules, as the entirety of the service combatant fleet is designed overseas by an international designer. So firstly, we'll look at the DST Group rule set 3550, which is it's a guidance type rule set for the Royal Australian Navy, and it's based on anthropometry data, which is particular to the REN workforce. It's human factors engineering based on this anthropometric data, and the idea of the rule set is to provide design guidance for acceptable size and spacing requirements, particularly for the REN. So as an example of how we have used this recent rule set, I would say recent, it was actually developed in 2015, and then the anthropometric data, and then I think 2018 or 19 it was made available. But we recently used it on a study because we're heavily involved in the Eurofura class OPVs, and we're engaged by Lursen to conduct an ergonomic study on the workstations for the OPV project. Workstations included the bridge, the operations room, and the machinery control room. And the aim was to verify that specified workstations complied with DST Group 3550 requirements. Sorry, I'll just let somebody in.
Yeah, no problem. No problems.
To identify any system design issues and to recommend any design alternatives. Okay, the assessment based on the DST Group requirements considered 5 physical aspects. That's fit, reach, clearance, vision, and posture. The assessment was guided by the following principles, which are based on the anthropometric data of the RIN. Which is in general designed for the smallest, which is the 5th percentile, designed for the largest, which is the 95th percentile, designed for the average, which is the 50th percentile, and the most common used and what we were guided by was designed for the range. So it's the 5th percentile female to the 95th percentile male is the range of anthropometrical data used. So the findings revealed non-compliance in quite a few areas, actually, from the baseline design. The fit was not within the target accommodation range. The chairs did not meet the height and width requirements. The inadequate forward and backward pan, which is movement. Improper positioning of chairs in relation to the desks or the consoles. Inability to reach the far end of the console while seated. Insufficient clearance hindered the rotation of chairs. And the most notable is the helmsman console on the bridge. It failed to meet SOLOS regulations due to poor visibility of the bow and the horizon while seated. And that was for the 5th percentile female. So you can see this is the original design for the 5th percentile female and the view of the helmsman over the bridge, which didn't meet SOLOS requirements. This was the acceptable new height and needed, and you can see in the next slide the actual difference in field of vision and requirements. So recommendations were made and implemented to optimize ergonomics in line with this DST Group 3550 and to accommodate the target population so far as reasonably practical. Recommendations included the implementing an alternative chair model that is better suited to the target accommodation range, modifying chair height and adjustability, addition of footrest, adjusting console height, installing deck rails for clearance and optimizing deck dimensions for improved reach and ergonomics. Allowances were made, so size increase over time for future crew, clothing, cushion compression and dynamic movement. There were some constraints, obviously, with implementing our recommendation. Obviously, there was limited availability of commercial off-the-shelf chairs, and cost, obviously, is a definite consideration, and commercial off-the-shelf chairs were needed. So economic feasibility, custom-made chairs and console height adjustability was not feasible. So we did have to make some compromises, obviously, within our recommendations. So that's just an example, obviously, of how we used the most recent or most up-to-date DST Group design guidance, and we used it in a real design to update a design and using the RIN, or the Australian Anthropometrical data. So as an overview, the current surface combatant fleet, they're not designed within the Australian Navy or the DST Group anthropometrical data. The Hobart class destroyers were designed in Spain and they're based on the Spanish F-100 design, and even the Hunter class frigates are based on the UK design. So any ergonomics is based on anthropometrical data from these two countries. So it is quite important to have specific RIN anthropometrical data, which outlines physical dimensions and requirements of RIN personnel which can obviously optimize ship design specific for the crew utilizing the ship. So some benefits, obviously, of incorporating REN anthropometrical data, obviously, a tailored accommodation, workspaces, and equipment, enhanced safety, performance, and operational efficiency. So now let's go to the next rule set, which is often specified in any upgrade or naval accommodation project, and it is the main rule set for the Royal Australian Navy at the moment. It's the DEFOS 5000 accommodation requirements. Some extracts from this requirement, just to give a bit of context of the importance the REN place in their requirements on habitability. So the REN recognises the positive impact that appropriate habitability criteria and design practices can have. Good habitability standards are essential in ensuring that a ship's crew performs at its maximum potential. Habitability directly and indirectly influences the safety of the crew and the platform. And poorly designed and outfitted habitability spaces will lead to a crew that is unhappy with their quality of life. This will have several short and long-term impacts. This will directly impact on crew safety, quality of life, recruitment and retention, crew performance, and morale. So that's just a little bit of context. That's straight out of the REN habitability rules, the DEFOS 5000. So let's go to surface combatant crew size within the Royal Australian Navy, looking from the 1990s to beyond the 2030s, from the Anzac class frigates, the Hobart class destroyers, and the Hunter class frigates that are not yet in construction but have been designed. And also in there, you can see there is a proposed increase in the Hobart class destroyers from a total berthing capacity of 234 personnel currently to 264 personnel. And that's part of the accommodation upgrade study that was conducted. The trend is there's no real trend, certainly in a reduction in crew size. The trend really is, if anything, an increase in crew size or a status quo, basically, but there's certainly no reduction in crew size. So the engineering assessment that was conducted is an investigation of increasing the berthing capacity on the Hobart class DDG destroyers from 234 to 264 personnel. Hobart class destroyers, that's 3 ships in the Royal Australian Navy: HMAS Hobart, HMAS Brisbane, HMAS Sydney. Basically, the only blocks that were analysed for an increase in accommodation space were the junior and senior sailors accommodation, basically on 2 and 3 deck, below the main deck, both forward and aft of the machinery spaces. So this is accommodation spaces in the aft end of the vessel on 2 and 3 deck. This is also accommodation spaces on the aft end of the vessel on 2 and 3 deck. And this is accommodation spaces in the forward end of the vessel on 2 and 3 deck. So the scope of the task was the impact on ships' auxiliary systems from increasing personnel capacity by 30, impact on total ship's capability, impact on crew habitability, impact on equipment manufacture, and then some ROM costing for installation. All the required changes were assessed, obviously, against the current ship's baseline requirements, which was the baseline Hobart class platform ship specification. But the study also included and it prioritized the following rule sets. Obviously, it was asked to comply with DEFOS 5000 Volume 8 Part 1 accommodation requirements, the DST group requirements. So the 2 main Australian Navy requirements for accommodation spaces and habitability were specified, and also for air conditioning and ventilation, the ISO 7547 ships and marine technology air conditioning requirement was specified. So just an overview of where accommodation was upgraded. Basically, the ship is it's in service, so it's designed and built. So we were only changing 2 berth bunks to 3 berth bunks, and then within certain spaces, increasing locker capacity in those cabins. So you can see this is where the additional 30 personnel were contained. So some arrangements, say a PO's berthing number 1 arrangement, where there is 8 bunks in there. So that's 2 berth bunks, and they were being upgraded. Oh, sorry, no, that's an additional berth bunk. But sorry, the next PO's berthing number 3. So that's 2 berth bunks, and some of the bunks were changed to 3 berth bunks. So yes, so PO's berthing number 3, 1 bunk obviously was changed to a 3 berth bunk from a 2 berth bunk. So that's where we got an increase in accommodation. And then 1 extra locker was needed in that compartment. So PO's berthing number 1, as you can see, 2 bunks were changed from 2 berth bunks to 3 berth bunks. So that's where the increase in accommodation was obtained. Auxiliary services analysis was also conducted. So the impact on the ship's grey water and black water analysis, potable and hot water analysis, HVAC analysis, laundry space, electrical systems, non-combustible garbage analysis, and endurance analysis. So grey and black water analysis, the ship's grey and black water had enough capacity to comply with ship specification and DEFOS requirements for the increased number of personnel. So that still passed, actually. Potable water did fail, and additional potable water was needed to meet endurance requirements. And the hot water analysis passed. There was sufficient capacity for ship's hot water. HVAC analysis. Well, HVAC analysis, a modern ISO standard was specified for the HVAC. So a lot of the baseline HVAC requirements were not met, which didn't meet the outdoor air requirements. So obviously any upgrade as well did not meet the HVAC requirements. Laundry space requirements. The current baseline requirements for communal laundry failed in the drying capacity. So any upgrade also failed in drying capacity. So increased drying capacity was needed to meet laundry space requirements. Endurance analysis, obviously when you're increasing capacity by 30 personnel and the ship's storage space is unchanged, because you can't change the storage space of an existing design. So endurance was reduced by 4 days. Habitability assessment was also conducted, and the DEFOS 5000 was the guiding document for conducting quite a detailed systematic habitability assessment, which assessed the internal environment of the upgrade, the ship's configuration, sleeping arrangement, ablutions, food services, recreational arrangements, office arrangements, and emergency equipment. So the main requirement, or the guiding quantifiable requirement for cabins, was actually deck area per person. So a guiding requirement in the DEFOS is 1.6 meters squared of a deck area per person, not including obviously the bunk and lockers, storage space. So the current requirements, or the current baseline design, does not meet that requirement. You can see the deck area per person in the fourth column there of the initial arrangement, and most of the cabins are well below that 1.6 meters squared deck area per person. So any upgrade obviously doesn't meet that requirement either. So it was not possible to meet that requirement. Ablutions, the number of toilets, wash basins, and showers didn't meet the requirement, obviously, of the number of specified toilets per 5 or per person on board, number of wash basins as well, and number of showers. So yeah, in certain areas that modified design didn't meet the DEFOST requirements. Food services requirements included the baseline requirement of store space to meet a ship's endurance requirement of 34 days. So as previously said, the increase in personnel by 30 reduces the ship's endurance to 30 days as there is limited space to increase food storage capacity. Ship's recreational arrangements, CPO's mess room and living room does not meet the ship specification requirements when the increase in number of personnel occupying the spaces and existing laundry facilities, as I specified, doesn't meet the requirement in the DEFOST for dry capacity. Emergency equipment increase by the increase of 30 personnel. The time taken for evacuation was estimated to be obviously increased, and the number of life rafts needed increased by 2 actually. So 2 additional life rafts were needed on either, or 1 on either side of the vessel for the additional 30 personnel. So just back to a previous slide now, going back to surface combatant crew size. So it's there's certainly no trend in a reduction in crew size over the Navy. We've looked at this particular study on the Hobart class destroyer, an existing design, and we've looked at an increase in personnel. It hasn't been implemented, but we've certainly looked at it, and we have looked at an increase in personnel for other REN ships as well recently. So the trend does seem to be for an increase in crew size, but certainly no reduction in crew size over time. Now, looking at the commercial sector, it's hard to find obviously direct comparisons between a naval vessel and a commercial vessel because they're different vessel types with quite distinct different mission profiles. But one vessel that a comparison potentially can be made is the RSV MRINA. It's a scientific research vessel operating out of Hobart. It's a multi-purpose, very complicated vessel. It's an icebreaker. It's a DP3, I think, notation. So it has a number of thrusters, very maneuverable. It has, I think, 21 different modes of operation for propulsion. It's got a hybrid type propulsion system where electric motors running off the main gearbox can be used as electric motors as a booster mode to provide increased speed. They can also be used as a loitering or silent mode for slow speed, quiet operation, and that actually can also be used as generators. So the main generators on the vessel can be shut down, and the engines can be used as generators for hotel load on the vessel. So it's a multi-purpose, very complicated ship type. It's one of the most complicated ship build that the shipbuilder Darman has built. That's something that that Darman told us, obviously, because we do work a lot on this vessel as well, as it's operating in Hobart. And the crew size for the RSV MRINA is a total of 32. So a much smaller crew size for a very complicated multi-mission type vessel, an icebreaker operating between Hobart and Antarctica. So looking at some crew differences, obviously, if any comparison between naval vessels and commercial vessels, you need to look at some crewing differences between the two vessel types. And this, I think, is a good explanatory overview of the structure of crew between the two. So the naval vessel they do have more lines of departments. I suppose they have a weapons electrical department, which is different to any commercial vessel. That's particular to a naval vessel. They have an engineering department, of course. They have a navigation department, a deck department, supply, and a hospital or medical department. A commercial vessel, the RINA, also has a deck department, an engine department, has a cook. There is a medical department on the RINA as well, actually, but definitely the lines of management are much less. So the commercial vessels have been able to reduce obviously the number of layers of management on the vessel, and being able to delegate responsibility obviously much lower. So there's much less chains of management and much higher levels of responsibility for personnel on the commercial vessel. A naval vessel still has obviously a very bureaucratic type organizational structure with various lines of management between heads of department to the bottom level, seaman level, able seaman level. So quite clear differences in the structure and organization of the vessel and crew. Some differences in terms of crewing evaluation. So in any new build or any vessel design, generally a flag state, definitely in the commercial world, flag state when ship owner looks at does a crewing evaluation. So it looks at the number of personnel needed for the mission of the vessel and so forth for that particular vessel. In the commercial world, it's very standardized and detailed, the crewing evaluation needed. You follow, there's an IMO resolution, A1047, which is the principles of minimum manning. AMSA also has a very detailed and stipulated document for conducting crewing evaluations for ship owners operating under the national standards for commercial vessels under AMSA, and also the standards for training and certification of watchkeeping, STCW standards are quite standardized and normalized throughout the world for commercial vessels, stipulated by the IMO. So the standards are common for all training, certification, and watchkeeping. And when conducting a crewing evaluation, it makes it quite easier to stipulate exactly what personnel are needed for that particular crew type and what the minimum level is. Regarding the Australian Navy, there is, or it was found to be very limited literature on conducting a detailed systematic crewing evaluation. There is an ABR 5225, which is the REN Marine Engineering Manual, which just stipulates really roles and responsibilities, but that's no longer valid, and it's been replaced by these two AMP documents, but they're not, it doesn't seem to be an overlying document or guidance on how to conduct a crewing evaluation study for a service combatant, for an RN vessel. So, okay, so looking at crew responsibility between Navy vessels and commercial vessels in any study. So in general, to summarize, Navy vessels, the crew conduct a lot more damage control activities. So it's a naval vessel. It should be prepared for war because it's designed, its operational mission is to go in a war zone. So in general, personnel, they're obviously they're ship operators. They have to safely navigate the vessel. They conduct a lot more damage control activities, preparing for war. There is most definitely minimal maintenance conducted by ship's crew on a naval vessel, and it's in general regulated by the Navy. In commercial vessels, they obviously They're operators, and they have to safely navigate the vessel. There is stipulated minimum levels of damage control activities conducted, but it's much less than a naval vessel. They most definitely do perform much more routine maintenance tasks, and the level of maintenance or repair conducted by a commercial crew is certainly much more than the naval vessel, and is regulated by either AMSA or IMO or international class societies as well. Looking at vessel management, so how naval vessels and commercial vessels are managed. This is an example. This is the Hobart class destroyers on the left-hand side, and there's a lot of different organizations involved in the vessel management. And for some reason, this is how vessel maintenance in general is managed on Hobart class destroyers, but the Navy is not in the center of the actual management cycle. It's a contractor with the DDG SPO, and every organization around the outside is this particular specialist organizations for particular areas of the ship. But yeah, that's how the Hobart class destroyers are currently managed in terms of operation and maintenance of the vessels. In the commercial worlds, there is far less organizations involved. Generally, the organization that manages the vessel maintenance is the same organization as the crew in general. And in general, this is the MRINA again, to draw the comparison. So the MRINA has a ship owner, which is the Australian government in the Antarctic division, and it has a ship manager and crew, which is a Serco. So there's two organizations involved, ship manager and ship owner, basically. So in general, to get work done, or to get quick turnaround of operational maintenance activities, there's far less organizations involved on the commercial side. So in general, it's a far more efficient operation. Some design differences when we're looking at differences between commercial vessels and naval vessels. Obviously, warships, they're designed to go to war, so they have a certain level of military capability, and they're an insurance policy of the nation. They're operationally, in general, cost effectiveness is not the highest priority compared to a commercial vessel. They're not for profit, obviously. They're certainly multifunctional, and so they can be difficult to optimize, and they do have a very high survivability requirement within the design. So hence, that's reflected in an operation, as we've spoken about much more damage control activities conducted by crew, but in a design, survivability is a big key characteristic of any service combatant design. So some technical challenges with the naval vessel design, obviously, it's combat system requirements, and the integration of topside design and combat system, the management of information, software on the vessel, and so forth. Much higher manning levels, as we've seen, and obviously survivability. Just as an example, an overview, the integration on a warship and topside design. So in general, a commercial vessel, obviously, it's designed for, the MRINA is not single mission, it's multi-mission, obviously, but topside design is not as important on a commercial vessel compared to a naval vessel. The various arrangements of combat system and communication equipment and the top side of a Navy vessel can actually dictate, in some service and combatant designs, vessel principal particular characteristics such as length and beam and so forth. So it's quite important, the topside design also on a warship. You would call that payload in general on a commercial vessel, but it's the layout and topside design of a servicing combatant is very important, and it's a distinct characteristic that needs really some attention compared to commercial vessels. So this is in general the design dilemma that we've come up with in general. So is crew size, habitability standards, because we've been stipulated certain Australian habitability standards that are just impossible to meet on a design that was that's already been built, obviously, and it hasn't been built in line with Australian habitability standards. And then obviously ship capability. So what is the compromise? In the Navy, the compromise is quite clear. Habitability standards are not met. And capability is maintained or enhanced, and crew size has stayed the same for the last 30 or 40 years. Commercial ships, habitability standards are very high on commercial vessels. There's generally single berth cabins, rarely double berth cabins on commercial vessels. Capability is of utmost importance. So capability has not been compromised either, and crew size has been reduced. So commercial ships have severely reduced crew size over the last 30 or 40 years to as low as 32 personnel on the MRINA as stipulated, but a lot of single mission commercial vessels out there today operating with a crew of 20 or below. So crew size has been reduced quite substantially in commercial ships, and the main enabler, we should say, for a reduction in crew size is machinery automation and the automation of equipment on the vessel, and personnel are still needed on the vessel to operate machinery, but because of such automation, less personnel are needed. So what is the compromise? Obviously, in this dilemma, crew size is reduced or capability is reduced on the same platform. So we had a look at the same study, but we actually looked at it from a different perspective. And why don't we look at the current DDG design frigates, and why don't we look at a design that does meet habitability standards? What crew size would that entail, and what sort of characteristics of the ship would we have if we did meet habitability standards? So the next small design study was looking at the same berthing space as the previous study on the DDG destroyers, but we looked at the number of bunks needed per cabin to meet habitability standards. So there was actually quite a substantial reduction in crew size when we looked at the senior sailors and junior sailors cabins, and we were able to halve the number of junior sailors and senior sailors there from 201 down to 92 as well. We also looked at officers' accommodation, but actually the officers meet the DEFOS standards. So it's only junior sailors and senior sailors that don't meet the standards. So we looked at the number of personnel and the arrangement of current berthing spaces to meet the standards. Looking at this reduction in crew size, so it was a total reduction of 234 personnel, to 125 personnel. So the endurance of the vessel increased from 33 to 62 days. So you've got an increase by a factor of 2 almost of endurance. Another way to look at it, obviously, or the food storage capacity needed to meet the current endurance reduced from 117 meters cubed to 65 meters cubed. So if you wanted to maintain the current endurance requirement of 34 days, then the food storage capacity needed is much less. Looking at potable water storage capacity and drinking water storage capacity and hot water consumption, but basically the requirements reduced by a factor of 2, which also reduced hotel load by approximately 180 kilowatts. Grey water capacity and storage tanks reduced by a factor of 2. Ship sewage treatment plant can be reduced by a factor of 2. Looking at HVAC requirements, HVAC system can be greatly simplified with the capacity and sizing of air handling units and fan cool units throughout the vessel. And the numbers can certainly be reduced. It wasn't quantified exactly by how much, but they certainly can be reduced and simplified. Laundry capacity can be reduced by a factor of 2 for both communal and recreational laundry spaces. Galley size and capacity can be reduced by a factor of 2 with the reduction in personnel, and messed area and dining area space also requirements were reduced. So looking at the design again for a reduction in crew size from 234 to 125 personnel, certainly range and or payload can be increased. It needs to be quantified. This study only looked at the existing design. So if it was done in a new design and the full design spiral was followed, then certainly range and or payload can be quite significantly increased, but also optimized within the vessel mission. But it certainly needs to be quantified. So conclusions and recommendations. So a reduction in crew size can allow a surface combatant to achieve modern habitability standards without necessarily reducing capability. In fact, in a lot of areas, as we've seen, it can quite substantially increase capability. What does compliant habitability standards mean for the crew or the ship? Well, this is straight from the DEFOS, but it can have a positive effect on crew safety, quality of life, recruitment and retention, performance and morale. So crew performing to their potential is maximum ship capability in general. I think it was quite clear from the study that habitability standards cannot really be retrofitted to existing designs without major compromises. Trying to retrofit habitability standards is extremely difficult if it's not implemented in the design from the outset. If implemented in the design from the outset, compliance with modern habitability standards can provide potentially ship-wide and fleet-wide capability increases. And this, in a design from the outset, obviously range, endurance, and firepower or combat system capability of the vessel can really be optimized for the fleet requirements and ship requirements as well. So this is the small compromise that was found: crew size, habitability standards, and ship capability. So this study was conducted purely looking at habitability standards. Some sort of crewing evaluation really needs to be performed against a compliant design to really find the correct compromise in this small design dilemma between crew size, habitability standards, and capability. I think it is quite clear that currently the pendulum is a little bit too far towards compromising habitability standards and maintaining crew size. And it would be very interesting in conducting a crewing evaluation if crew size can be reduced to allow for better habitability standards of crew. And that's a recommendation of the study, obviously, that a detailed crewing evaluation is performed against a compliant design.